Okay, so in this problem we have a spool of mass m and a centroidal radius of gyration kg and an outer radius of r and an inner radius of little r to which a constant force F is applied at an angle of theta around the inner radius. We're told that the spool rolls without slipping on a rough horizontal surface. And based on all this given information, we're asked to determine the angular acceleration of the spool as a function of the angle theta. Okay, so to help us out here, because we're trying to find an angular acceleration, I know I want to actually draw a free body diagram and solve this via Newton's second law. And so if I do that, what I'm going to have here first of all is the force due to weight, which I can actually call just mg in this case. We'll have some normal force on the ground n. I'll have some friction force here, which I'll call little f, and I'm not going to pay particular attention to which direction it is in this case because we're at an object rolling without slip. And I'll have this applied force here, F, which we know is oriented at an angle theta with respect to the x-axis, if I define x and y to be like so. Now in terms of kinematics, we know this thing has the ability to translate, and it'll purely translate, so I'll have some magx, and we have the ability to rotate, so I'll have also some ig alpha. So with those things in hand, I can go ahead now and apply my kinetics equation. So if I start by summing forces in the x direction and setting that equal to m times agx, what I'm going to get here is that the friction force plus the cosine component of the applied force is going to equal m times agx, and we can call that equation 1. If I sum forces in the y direction here and set that equal to 0, because we know the center of mass of the disk is not going to move up or down as this thing rolls, I'm going to have that n plus f times the sine of the angle theta minus the weight is going to equal 0, and we can call that equation 2. I can also sum moments, in this case maybe a convenient point is about the center of mass, and set that equal to I about g times alpha, and I'll do so in a counterclockwise positive sense, and if I do this I'll have little f times the big radius plus big F times little radius is going to equal I about g, which because we're given a radius gyration will be given by m kg squared times alpha, and we can call that equation 3. Now if we stare at these equations 1, 2, and 3, we realize we still have a few too many unknowns, namely I don't know F, I don't know agx, I don't know the normal force n, and I don't know alpha. How we're going to get those is by utilizing some kinematics information. So in this problem, for example, what I can say is that ag is going to equal the acceleration of point C, the point that's in contact with the ground for which we have a no-slip condition, plus the angular acceleration of the drum cross r of g with respect to C, minus omega squared times r of g with respect to C. Now if we go back and read this problem statement carefully, you'll note that it says nothing here about this object initially being at rest, and so we don't have to worry about that. And so I'm going to plug this in assuming omega is an unknown as well. So what am I going to have? Well, I'm going to have that agx in the I, we've already determined the y component of acceleration for g0, is going to equal ac, which I know has to be purely in the j, plus alpha in the k, cross r of o with respect to c, which is a distance r in the j, minus, and I should say this is not o, but actually g with respect to c, my apologies, minus omega squared times r of g with respect to c, which is r in the j. If I expand the right hand side here, I'll have ac in the j, plus k cross j is going to give me minus I, so I'll have minus alpha r in the I, minus omega squared times r in the j. If I pull the I component off here, I'm going to have that agx is equal to minus alpha r, and if I pull the j component here, I'll have that 0 is equal to ac minus omega squared times r. And we can call these equations 4 and equation 5 respectively. Now again, let's go back to the problem statement for just a split second here. And if we do so, you'll note that we're trying to find the angular acceleration of this drum as a function of the angle theta. This is kind of an interesting result here, and so I'm actually going to solve this one out and work it with you. And so the way I'm going to do that, after I pan, and sorry for the slow pan this morning, I'm going to start by plugging equation 4 into equation 1, and so if I do that I'm going to have f plus big F times the cosine of the angle theta is equal to m times agx, which is minus alpha r. I'm then going to take this and solve this for the friction force, little f, and so if I do that, little f is going to be minus f times the cosine of the angle theta minus m times alpha times r. If I take that result and plug it into equation 3, I'm going to now have f, so minus f times the cosine of theta times r minus m times alpha times r squared plus f times little r is equal to m times kg squared times alpha. Now here we can actually look at this equation and realize we only have one unknown, and so we can go ahead and solve for our result. So what am I going to end up with? Well, what I'm going to end up with is, moving like terms to the right side, f times r minus f times the cosine of theta times big R is going to equal m times r squared plus kg squared times alpha, which means that the angular acceleration alpha is going to equal f times little r minus big R times the cosine of the angle theta divided by m times quantity r squared plus kg squared. And if we want to make this in vector form, we can simply append the k. Now, why did I take the time to solve this when I often don't in the videos? Well, I want you to note very carefully here that if we look at the numerator of alpha, there's a term r minus big R times the cosine of the angle theta. Depending on the angle theta, what we'll realize is that this has the potential to have a positive or negative alpha. And that's exactly the case. If you apply a force to the rope as shown in the diagram and change the angle of theta, you'll actually find some values of theta for which this thing will roll clockwise, and you'll find some values of theta for which this will roll counterclockwise. It's a fun experiment to do. I encourage you to check out the videos of us doing so, if you can find them on your course blog. Alright, I think that's a good place to wrap up, everybody. I'll simply wish you the best of luck. Take care.